Same here. This is the basic exercise you can do. Find the greatest common divisor of 15 and 26. So here 15 and 26 having the factor 3 into 5 and 2 into 3, 2 into 13, and here they share no common factor as all. So greatest common divisor of 15 and 26 will be 1. And we can also say that because of the common factor 1 in 15 and 26, 15 and 26 both are co-prime or relatively prime numbers. So this is the concept of co-prime numbers when the common factor is 1. Same, find the greatest common divisor of 48 and 360. So here for the 48 we have the prime factorization in form of 2 into 2 into 2 into 2 into 3 equals 2 to the power 4 into 3, and 360 equals 2 into 2 into 2 into 3 into 3 into 5 equals 2 to the power 3 into 3 over 2 into 5. They both share factors of 2 to the power 3 and 3. So the greatest common divisor of 48 and 360 equals 2 to the power 3 into 3 equals 24. Turns out finding prime factorization can be time consuming. More efficient algorithms exist, one of which is the Euclidean algorithm. We have already seen the Euclidean algorithm. One of the division rule was if A divides B and A divides C, then A divides B plus C. So start by dividing the larger number by the smaller. 48 and 360. 360 equals 48 into 7 plus 24. 360 is the larger number in 48 and 360. So here 360 equals 48 into 7 plus 24. Then now any divisor of 360 and 48 must also divide 24, which is equal to 360 minus 48 into 7. Like here 24 is equal to 360 minus 48 into 7. But similarly also any divisor of 48 and 24 must also divide 360, which is equal to 48 into 7 plus 24. Thus the GCD of 360 and 48 must also be the GCD of 24 and 48. And so now we have a smaller number to find the GCD of, which is easier, and the GCD of 360 and 48 must also be the GCD of 24 and 48. So here continuing by the dividing the two new larger number by the new smaller number, 48 is equal to 24 into 2 plus 0. Here we have extracted 24 and 48 by using the larger number 360 in the form of 360 equals 48 into 7 plus 24, and 360 is equal to 48 into 7 plus 24. And also now we have the challenge for the 24 and 48, because the greatest common divisor of 360 48 must also be the greatest common divisor of 24 and 48, and this is easier to evaluate the greatest common divisor of 24 and 48. So we can easily see 24 is the greatest common divisor, and also by the division rule 48 is equal to 24 into 2 plus 0, and once you find a 0 remainder, the GCD is equal to the last non-zero remainder. There is an important fact underlying the Euclidean algorithm, the theorem. If A can be written as A equals BQ plus R, where A, B, Q and R are integers, then GCD AB is equal to GCD of BR. The Euclidean algorithm uses this string of equivalence until you get down to a zero remainder, and the GCD is the last non-zero remainder found. Why? Because is the last step, we would say that GCD of AB is equal to GCD of BR, but with R equal to 0, we know A is the multiple of B, and the GCD of two numbers where one is the multiple of the other is the smaller of the two numbers. That is the GCD of KB, B equals B, where K belongs to positive integers. In this example, related to the primes and GCDs, use the Euclidean algorithm to find GCD of 1001 and 1331. So first of all, we have to choose the larger number among 1001 and 1331. Here 1331 is the larger number. So here 1331 is equal to 1001 into 1 plus 330. Same here, 1001 is equal to 330 into 3 plus 11, and thereafter 330 is equal to 11 into 30 plus 0. The last non-zero remainder is 11. So the GCD of 1001 and 1331 is equal to 11. That was a lot of work. Let's make a computer to do it. We can simply generalize this form for finding the GCDs of the two numbers. The pseudo